Okay, any questions? No. So we have the test coming up on Thursday. The test is going to be mostly multiple choice. It's going to include chapter 7, 8, and 9. I decided not to put any chapter 10 material on there. This exam, for the free response, I'll probably have you draw something like the energy level diagram. And so what is the energy level diagram? Is the energy, when I ask people to draw it, sometimes they'll draw this, 1s, 2s, 2p. Is that the energy level diagram? No, this is going to be the orbital box diagram. This is not what I want. What I want you to draw is this, 1s, 2s, 2p. It's going to be for the multi-electron species. The single electron would just be a straight line. Dot, 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 all the way up to 4p. And so you should be able to draw that. And you have to be careful when you draw this. You have to make sure, for example, a lot of people, when they write the 4s, they'll put the 3D, 3D is supposed to be higher in energy, but sometimes they'll make it the same energy or below. I don't want to see that, otherwise I'll mark it wrong. The 3D has to be higher in energy than the 4p. And so you have to know how they fill and then draw it like that. And so this is an energy level diagram, because here we plot energy on the y-axis and then we show the levels. Not like this. I mean, energy is increasing this way, but it's not exactly the same thing, because it doesn't give us the relative energies here that we're looking for. Also, you're going to have to be able to label the orbitals. Do you know how to label the orbitals? Well, this is one way. There's another way to label the orbitals. What is that? With quantum numbers. So this would be the 100 orbital, right? The 200, etc. And so be able to label those. And then when we fill them with electrons, you'll have to be able to, determine the quantum numbers for the electrons. And so if I'm filling that, this first electron would be 100 plus 1n, etc. So for the 4 quantum numbers, N, L, M, and S. What else should you know? You should know things like the shapes, an s orbital, as far as a cloud distribution goes, is spherical. And then you could have a boundary, 90% boundary, so you get 1s orbital. P orbitals, kind of dumbbell shape here. D orbitals would be like a clover-leaf shape. P, D. These are crude drawings. All right, any questions on the test? The calculations, like chapter 7 type calculations, you'll do multiple choice. Just pick the best answer. The equations, for the most part, I'm going to give you the equations and the constants, except some equations I'm not going to give you. For example, there are n squared orbitals for every n. That equation I'm not. That equation you should be able to figure out anyway based on the chart there, or that there are 2L plus 1 orbitals in every L level, that kind of stuff. Those types of equations I'm not going to give. The type of equations I'll give you are like the Q, Q is equal to amount times C times delta T, and R is 8.3145 joules per mole Kelvin, that kind of stuff. The basic equations of thermal. All right, any questions about the test? No? All right. Today we're going to talk about bonds. We're going to talk about covalent and ionic bonds. Okay, why do bonds form, you know? If you look at most of the substances on the periodic table, most of them occur in nature as compounds. You know? Some of them do occur as elements, like gold you can find as elemental gold. You know, copper you may be able to find. You know? But a lot of the elements are more stable as compounds rather than elements. And so when we form bonds, we typically think of stability. You know, it's going to be more stable. And so why do things like molecules form? Molecules typically form because it's more stable, you know, stronger bonds. And so we can get an idea about the bonding by looking at one of the periodic trends, which would be something like melting point. If we look at melting point, we'll go on the fourth or third period. Actually, let's do third period, since this is what's in your book. Sodium, magnesium, aluminum. Comes after aluminum, silicon, and then phosphorus, sulfur, chlorine, argon. If we look at the melting point for this, the melting point shows a periodic behavior, and it's repeated. So, you know, when we look at the melting point for this, you know, sodium has a fairly low melting point. Sodium melts at under 100 degrees C. Argon melts well below room temperature because argon and chlorine are gases, so these have the lowest melting point for sure. And sulfur melts at around 100. And phosphorus, depends on what form of phosphorus you look at, but silicon peaks way up there. So something like this. This peak pattern's repeated. I should draw more broadly shouldered, like this. But it just shows a peak and melting point there. And so if something's hard to melt, that means the bonds are quite strong, you know, the bonds holding it together. And so this tells me that silicon has some strong bonds. Either strong or overall it's just strongly bonded. And the same pattern repeats. For example, if you look at lithium to neon, you know, lithium has a very low melting point. Neon has a very low melting point, but carbon has a very high melting point. You know, carbon would be in the form of graphite or diamond. It's very hard to melt. It's very hard to melt silicon too. It's extremely tough to melt that because you need such high temperatures. When we look at this, you know, this is the third period. And we look at this in terms of valence electrons. You know, valence electrons are the electrons in the outermost shell. And sodium has 1 valence electron, magnesium's 2, aluminum's 3, silicon's 4, 5, 6, 7, 8. 8 electrons would be a filled valence shell, like argon. And so silicon is 4 valence electrons, but when we look at silicon, you know, normally we would write it like this. You know, there's 4 separate electrons. Oh, there's the table. Looking for that this morning. Okay, so silicon has 4 valence electrons, but when we look at silicon's energy level diagram, you know, silicon's energy level diagram would be neon as far as the core goes, and then we have a 3s, 3s2, 3p2. And so 2 of these electrons should be paired in a 3s orbital, and the other 2 are singles in the 3p. But why do we write these as 4 unpaired electrons when clearly 2 of them are paired? And the reason we write this as 4 unpaired electrons is because of this. If we promote one of these s electrons up to a p orbital, then we'll get 4 unpaired electrons. Now, why would we want 4 unpaired electrons? The reason we would want 4 unpaired electrons is that way we can form 4 bonds here, you know, if these electrons get shared. And so when I look at this valence shell, the valence shell has 4 valence electrons. Whereas over here, if I left one of them paired and then two unpaired, then this could only form two bonds because of the sharing requirements for the electrons. So just two bonds can come in here. Maybe a third bond can come in if both electrons come from another species. And so this promotion of the electron is going to cost energy, but you get the energy in return when you can maximize the bonding. And so the reason why this peaks here is because now we've maximized the bonding here. You know, phosphorus is only going to form 3 bonds typically, sulfur 2 bonds, chlorine 1 bond, aluminum 3. These form metallic bonds. And so here we see a max in the number of bonds that can form. And therefore, you know, if we've got 4 bonds holding everything together, it's going to have a very high melting point. And so typically when we think about silicon, you know, silicon's going to have a structure like this, where there are going to be 4 bonds to other silicons, and these silicons in turn will have 4 bonds or 3 bonds to other silicons, so altogether 4 bonds. And so we expand this lattice. You know what type of lattice this is? Is that an ionic lattice or a network covalent lattice? That's a network covalent lattice. It's very hard to break apart that lattice. And therefore the melting point is extremely high. Diamond has a lattice like that too. And so we form bonds, and those bonds help stabilize things energetically. So let's take a look at these bonds in general. The span of bonds are going to range from ionic, you know, to covalent. And so let's take a look at this range from ionic to covalent. So if I take sodium ion, or let's not go with ion. Let's go with sodium, the element. Sodium, the element, has 1 valence electron. And then react it with an atom of chlorine. Chlorine has 7 valence electrons. Chlorine's a strong oxidizer. Sodium's a strong reducer. What does it mean to be a strong reducer? It means that it gives up electrons easily. Well, if you think about sodium, sodium has an ionization energy, I1, of about 500 kilojoules per mole. 500 kilojoules per mole is a significant amount of energy. And so for chlorine to take this, you know, it has to overcome the ionization energy of sodium. That is, sodium doesn't really give up the electron, it just doesn't hold on to it tightly enough. So that something like chlorine can come over here and pluck it off. Chlorine comes over here and plucks off the electron, then we end up with sodium chloride. Sodium has no valence electrons and positive charge. Chloride has 8 valence electrons and a negative charge here. So this is now what we call an octet, a filled valence shell on chlorine. All right, here we have an ionic bond. And we just show an ionic bond like this, the 2 ions adjacent to each other. Really, when I take a mole of sodium and react it with a mole of chlorine atoms, I don't form a mole of ionic bonds. This is a bit tricky. Sodium chloride has a very high melting point as well. And it's because when sodium chloride forms, what happens is we'll have sodium and chloride ionically bond like this. Which one is sodium, which one's chloride? Chloride's the big one. And so it actually reverses, because as far as atoms go, is this right? Sodium is a bigger atom than chlorine? Is that right? Yes, for atoms, yes, and then it flips. So that's right. Well, when we form, we don't just form one ionic bond, because each sodium ion will try to surround itself with as much negative charge as possible. So it fits 4 here, 1 in the plane above, 1 below. And each chloride ion will try to fit as many sodium ions around it as possible. 4 in the plane, 1 above, 1 below. And so really, as far as ionic bonds, if I have a mole of this, I'm going to get 6 moles worth of what we call nearest neighbor ionic bonds here for each ion. And then the next nearest neighbor would be a repulsion, you know? But the next nearest neighbor would be an attraction. And so what we do is we sum up all these attractions and repulsions, and net attractions are going to be stronger. And so what we have there is we have an ionic lattice. Ionic lattice. You know, and again, this whole idea of trying to maximize the bonding. Maximizing the bonding is going to help stabilize the compound. And so here we'll try to form as many bonds as possible because that's going to help, again, stabilize it. And so we generate an ionic lattice. Well, let's continue here. Sodium's ionization energy is on the lower side, 500 kilojoules per mole. If we compare it to hydrogen, what's hydrogen's ionization energy? Roughly? Hydrogen's ionization energy is about 1,500 kilojoules per mole, and just roughly. And so it's about 3 times harder, or requires 3 times as much energy. More like 1,300, so let's call it 1,500 to make it easy. And so, yeah, it's going to be harder to pluck the electron. And it turns out that chlorine doesn't have quite enough oxidizing ability. In other words, another way of looking at this is chlorine's ionization energy is much higher. Chlorine's ionization energy is considerably higher, meaning Z effective is very big. If Z effective is very big, then that's going to have an attraction on this electron. But chlorine's is not big enough. And so what happens is the hydrogen doesn't completely let go of the electron. It just... And so over here, sodium completely let go of the electron. So that electron cloud, electron density is, you know, pretty much concentrated on chlorine. Over here, chlorine's stronger than hydrogen, but not strong enough to pull it completely off. And so what happens is hydrogen holds on to some electron density here. So we get something like this. This is called a polar covalent bond. All right, now if I have another chlorine here, a chlorine versus a chlorine, chlorine has a very high ionization energy. And if chlorine tries to take an electron from chlorine, it's not going to be successful. In fact, this chlorine, both of them want an electron, so let's try to take it. And what results is something like this, where since they're both equal in strength, it's going to be a tie. You know? And so we end up with a bond that's very symmetrical like this. That is, the electron density is evenly shared between the 2 chlorines, and we call this a non-polar bond. Non-polar bond. So rather than using ionization energies, which we could use ionization energies to give us an idea. Because ionization energy is going to depend on Z effective. You know, Z effective is the nuclear charge that's felt by the outermost electron. And Z effective is going to have the pulling power for the electrons. And so this is kind of like a tug of war. Which one has a higher Z effective? You know, they're pulling on the electron. Turns out chlorine does. Here they're an even match. Here, sodium is not quite a match for chlorine. But rather than using Z effective and ionization energy, there's an easier one we can use, and that's electronegativity. So let's talk about electronegativity here. Electronegativity is the ability to attract an electron. And so the higher the electronegativity, the greater the ability to attract an electron is. Which is slightly different than electron affinity. Electron affinity and electronegativity you would think would be the same thing, but they're slightly different. You know what the difference is between electronegativity and electron affinity? The difference is electronegativity just looks at attracting an electron, whereas electron affinity looks at attracting and holding the electron. And so, you know, you'd expect fluorine to have the highest electronegativity and the highest electron affinity, but it turns out that fluorine doesn't have the highest electron affinity. And it's because its orbitals are kind of small compared to chlorines. And so electronegativity, it turns out, is easy because fluorine does have the highest electronegativity. It's given a 4.0. This is Pauling's electronegativity scale. And so fluorine's at the top of the chart, a 4.0. What's at the bottom? Which species do you think has the lowest electronegativity? Lithium? It's not lithium, actually. Cesium. Cesium, francium's radioactive, so I'll just ignore it. Cesium. Cesium's bigger, you know, bigger atoms. So cesium electronegativity is like 0.7, 0.8, something like that. And so the electronegativities range from about 0.7 to 4. And so this is talking about the pull on an electron. What about hydrogen? Where do you think hydrogen lies? Actually, let me leave this up here. There's one other thing that's right here. We can see increasing polarity. 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 You know what polarity is? Polarity is like polar. Polar. For example, there's something called a dipole. A dipole has two poles, like a north pole and a south pole. You know, the Earth's magnetic field is dipolar. Electric fields are also dipoles as well because there's a positive pole and a negative pole. And so when we're talking about polarity here, you know, we're looking at poles. For example, over here, this is negative, this is positive. Over here, these are both 0, 0, and 0. Here, they're somewhere in between, you know, because the chlorine has built up some negative charge density over here because the electron density is going towards the chlorine. And therefore, the chlorine has an excess, but not a complete, you know, electrons worth, but an excess of electron density here. Hydrogen has a deficit of electron density here. So hydrogen is positively charged, chlorine's negatively charged, but you know, we call these partial charges like delta plus and delta minus. Are you guys familiar with delta plus and delta minus? Yeah? No? Delta plus just means a positive charge less than +1, let's say. Yeah. Partial charge, it just means partial charge. Not a complete charge. A complete charge would be +1. You know, that would be what we'd call a full charge. But this would be a partial charge. Here, what's the charge on the chlorines? The charge on the chlorines is going to be 0 and 0. And so we can see the increasing polarity as we go up, as the charge separation becomes more significant. Then increasing polarity, we give a name to that. You know, when something becomes increasingly polar, we can think of it in terms of quantitatively ionic character. So let's look at percent ionic character. For this one here, you know, we'd say that chlorine-chlorine would be 0% ionic character. This is no polarity. You know? And when we're looking at ionic compounds, these are going to be the most polar. And so as we go up, you know, this would be about 100% polarity, or 100% ionic character, because sodium chloride is an ionic compound. There's charge separation there. And here, you know, the percent ionic character here is going to be greater than 0, but less than 100. And so somewhere in between here would be the ionic character. For that. What we can do is we can look at the difference in electronegativities, because you know what is the biggest difference in electronegativity we can have? And that's delta En. Delta En, you know, if we're looking at cesium, I'll just do the absolute value here, and fluorine, you know, the biggest one is going to be fluorine and cesium. It's 0.7. And so it's going to be about 3.3. There's our delta En. You know, that's the biggest difference in electronegativity, which is the biggest difference in the strength in the tug of war for electrons. And so the delta En of 3.3, that should be pretty ionic. In fact, that's the most ionic we can get. And so we're going to make up a plot here concerning percent ionic character versus delta En, the difference in electronegativity. And it's going to range from 3.3 to 0. You know, for example, delta En for chlorine, Cl2 should be 0. If we have a delta En of 0, then the percent ionic character should be 0% ionic character. 0% ionic character is 100% covalent. You know, and then we'll cop out 100 here. And so we'll take a look at the trend for this. And the trend is going to be something like this, where as the difference in electronegativity increases, so does the percent of ionic character, and then it tops out here. This will be the trend line for this. But when we look at the individual data, you know, and how can you determine the percent ionic character? You know, what are the ways to do it? Different ways of doing it. For example, if you have a dipole, you know, positive pole and negative pole, there's ways you can measure that experimentally. You know, it's called the dipole moment, is it? And you can measure it in electric fields. And so from the dipole moment, we can determine what the charge on those atoms are. You know, is it a full +1 or is it a partial charge? Or we can calculate it theoretically, you know. But anyway, we can get this percent ionic character. If we calculate it theoretically, we can calculate it from quantum mechanics, or we can measure it measuring the dipole. And so we'll see some data out here. So it'll be like this, you know. And you look at this data, and does it look like a good correlation? What do you think the R² value is? R², if every data point, which are these x's, if every data point lies on the blue line, then the R² value for the blue line is 1. You know, that is its perfect fit. But when you look at this data, the data is pretty scattered all over the place. Right? And so the R² value isn't going to be so high. And so there is a correlation here, but the R² is not great. But R² is poor. And so there must be other factors, you know, other things going on than just the percent ionic character and delta En. And there is. With the difference in electronegativity, they're better scales. For example, this is Pauling's, but they're more accurate scales. You know, Pauling's is kind of the basic electronegativity scales. The more accurate scales of electronegativity factor in two things: the oxidation state and the number of bonds. You know, to get a more accurate picture of what's going on. But anyway, the correlations here, it's a rough correlation, but you can see, as as the difference in electronegativity grows, so does the percent ionic character. And so, for example, in cesium fluoride should be the most ionic compound, so that should be the one closest to 100%. Cesium fluoride. Here we'll just draw one formula unit of it. That would be it. Okay, so let's take a look at some of these. I forgot to mention a couple of things. All right, so what we'll do is we'll put this into regions. So these ones here with the high delta ENs are going to be called ionic. These ones here will be, non-polar covalent. And then in between non-polar covalent and ionic, we have polar covalent bonds. Polar covalent bonds. And so typically in Chem 4, people memorize it like this. Ionic bonds occur when you take a metal and a nonmetal. Metals have very low electronegativities, nonmetals have high electronegativities. And so those yield the highest delta ENs. If you take two nonmetals that are kind of far apart, then you'll get polar covalent. If you take two nonmetals that are close together, then in terms of electronegativity, you get nonpolar. And so we'll take a look at some examples of that now.
Does electronegativity also play a role in metallic bonds?
Not really. It does in a way, but people don't discuss electronegativity in terms of metallic bonds. And so we aren't going to use electronegativities to analyze any of the metallic bonds. All right, let's look at some examples here. Examples would be something like this: hydrogen. What's delta EN here? The delta EN, there's no difference. They're both hydrogen atoms. And so this would have a delta EN of 0, which means its percent ionic character is 0. And so this is 100% covalent. We can think of other things that are 100% covalent as well. So another example would be diamond. And so this is molecular here. This is a molecular element. You can have molecular compounds as well. Diamond is this type of structure in which the carbons, kind of like silicon, would be bonded to 4 other carbons, which in turn are bonded to 4 other carbons. And so we set up a lattice here. This would be called a network covalent lattice. And a network covalent lattice like this, well, these are non-polar covalent bonds. Delta EN is 0 here. But sometimes, if we look at something like carbon and hydrogen in methane, are these bonds non-polar covalent, or are these polar covalent, or are these ionic? Well, it depends on the delta EN here. And so we look at the delta EN. For carbon, it's 2.5. 2.5 for carbon. For hydrogen, what's electronegativity for hydrogen? Now, hydrogen, is it going to have a low electronegativity like a metal, an alkali metal? It's over here, or high electronegativity like fluorine? The highest electronegativity is fluorine, and so it goes from cesium to fluorine. That is, as you go left to right, electronegativity increases, and as you go up, electronegativity increases. And so the trend is that it gets increasingly stronger in terms of electronegativity as we go up and right. although we have to eliminate these, because helium, neon, argon, none of these want another electron. They have a full shell. Full shell means an electron has to go in the next higher energy, which is not favorable. And so, what is it? Is hydrogen highly electronegative like fluorine, or does hydrogen have very low electronegativity like lithium? It seems to occur in both spots. And the answer is it's neither. Hydrogen actually has an electronegativity that's intermediate, right in the middle of the periodic table. And this electronegativity is between boron and carbons. And so hydrogen's electronegativity is 2.1. And so this gives us a delta En of 0.4. A delta En of 0.4 puts it around here. And it's going to have very low percent ionic. It's mainly covalent. And so this is what we call a negligible. The delta En is very small. And so what happens is we build up a very, very small positive charge on carbon and a very negative charge on carbon, and a very small positive charge on hydrogen. And so these are dipoles as well. There's two poles, a positive pole and a negative pole on each of these bonds. But these are negligible. In other words, they're negligible dipoles, or we say negligible polarity. And so since it's negligible polarity, it's essentially non-polar. And so if the elements are right next to each other, then most likely they can form a pretty non-polar bond. And we'll have some cutoffs here. And so our cutoffs are going to be about 0.5. 0.5 and below, we'll have non-polar covalent. And then 0.5, these are just crude cutoffs. To about 2, we'll have polar covalent. And above 2, it's ionic. Those aren't set in stone, nor is this correlation. The correlation's kind of, you see some things that don't quite fit our correlation here. Is R squared. But still, since there is a rough correlation there, we'll just call it. We'll leave it at that. All right, we can look at some others, for example, carbon dioxide. Carbon-oxygen bond is going to have a delta En in this range, in the polar covalent range. So, oxygen's more electronegative, so that's going to pull the electron cloud towards it. These partial charges have to add up to the net charge of the molecule, which is 0. And so in other words, oxygen is more electronegative, so if there's a tug of war for electron cloud or electron density, oxygen is going to be stronger. But it's not strong enough to completely pull the electrons off the carbon here. And so we end up with a polar covalent bond. Here we have a molecular compound, molecular compound. We can see this in network covalent compounds as well, like for example, silicon and oxygen. Silicon and oxygen is going to have a delta En between 0.5 and 2. And in silicon and oxygen compounds, we just have silicon bonded to 4 oxygens, and each oxygen is bonded to 2 silicons, and this extends in 3 dimensions. So this is called network covalent. And these are polar covalent bonds in here. When we get to delta En's greater than 2, then we're going to have ionic bonds. And so, for example, sodium oxide. Here, the sodiums are going to lose the electrons to oxygen. It's going to go 2 minus. So this would be 1 unit, and what we'd form is we'd form a lattice, like this. But here, we have ionic bonding, and ionic bonding, difference in electron negativity, sodium's too weak to hold on to the electron. Oxygen takes all the electron density here from this sodium, and oxygen's going to take all the electron density from this sodium. And then it has 2 lone pairs anyway, so it's got electron density here and here. When we look at the lattice is going to be an extended array of ions here, etc. Lattice. We don't form molecular compounds here, this. The reason is because you want to maximize bonding. If you maximize bonding, you try to put as many negatives around each positive and try to put as many positives around each negative. And you're going to generate a lattice like this. Metallic bonding, we aren't going to talk about until later. Okay, this deals with bond dipoles, If we look at the bond dipoles here, this is not a partial charge. These are full charges. So sodium has a full +1 charge. The oxide has a full -2 charge. These are partial charges here because the oxygen wasn't able to strip the electrons. If it could strip all the electrons away, it'd be -2. This would be -2, and the carbon would be +4. But since it wasn't able to completely strip it away, it's some charge less than -2, and this is some charge less than +4. If we want to figure out what the charges are, we can do that either by calculating theoretically using quantum mechanics or doing some measurements of bond dipoles. They call them dipole moments. And we can measure dipole moments, how strong that dipole is. Well, in addition to bond dipoles, we have molecular dipoles. Molecular dipoles can be measured as well. Molecular dipoles, to generate those are just equal to the sum over 3 dimensions of all the bond dipoles. And so looking at an earlier example of carbon dioxide has 2 bond dipoles. There are different ways of representing the bond dipole. The partial charges is not quite a full -2 because not all the electron density went there. This is not quite a +4. This is not quite, but it's somewhere in between 0, -2, and 0, and +4 for the charges. We can show that using arrows here. This says the same thing. That is, it says that the electron density is polarized towards oxygen. Polarized just means it's asymmetric. It's more towards oxygen than it is towards carbon. And so this tail here is a positive sign. So that's a positive tail. So that ends up there. So So we got a bond dipole pointed this way. Based on the structure of carbon dioxide, we have a bond dipole pointed in the opposite direction. And so when we try to figure out what is the molecular dipole for this, the molecular dipole is we add up the two bond dipoles. And when we add up those two bond dipoles, the molecular dipole comes out 0. When the molecular dipole is 0, we call it a non-polar molecule. We can have different structures like that. This is not an accurate 3D representation of this molecule. We can kind of figure out what this molecule is. This molecule is 1, 2, 3, 4, 5, 6, 7 carbons. You know, 7 carbons is called heptane. With heptane, you know, the single bonds are moving about, there's rotation, so this molecule is changing shape a little bit, depending on how the bonds are rotating. But do you think all the bond dipoles will cancel in 3 dimensions? Something like, no, it doesn't seem like it would, but we don't have to worry about that because all the bond dipoles are so small, they're negligible. And since, because the electronegativities of carbon and hydrogen are right next to each other, and actually quite close. And so carbon-hydrogen bonds are nonpolar. That is, the bond dipole is equal to 0. And so it doesn't matter what the shape is. If we sum up zeros, it's all going to come out 0. And so heptane's nonpolar. With something like water, you know, water is going to be quite polar. The bond dipoles do not cancel each other out in 3 dimensions. So if we look at water here, water is going to have a bond dipole pointing towards oxygen here and another one pointing towards oxygen here. And so if we sum up these two bond dipoles, we'll generate a molecular dipole. The molecular dipole, if this one's pushing this way, this one's pushing this way, the net is going to be like this. And so this would be the molecular dipole here. The molecular dipole. And so we call this a polar molecule. So those are nonpolar molecules, this is a polar molecule. So certain things we can figure out based on this polarity. For example, CO2. CO2 is nonpolar, water is nonpolar. So does CO2 dissolve in water? No, it bubbles out. Very little CO2 dissolves in water. Most of it just bubbles out because it's not very soluble. It's not very soluble because we have a rule. The rule is for molecular compounds, the solubility can be dictated by like dissolves like, or likes, like. And so, in other words, this is nonpolar, this is polar. And therefore, it's a mismatch from CO2. But, you know, heptane's a liquid too. Will CO2 dissolve in heptane? Yes. CO2's nonpolar, heptane's nonpolar. They like to dissolve in each other. And so CO2 wants to dissolve in nonpolar things like heptane, but not in polar like water. know, ammonia prefers water than heptane. Ammonia easily dissolves in water because ammonia is polar, water is polar, but ammonia is going to have a hard time in heptane. And so like dissolves like is what we use. How about CO2? CO2 is nonpolar. Is diamond polar or nonpolar? Diamond. Diamond's nonpolar. It's just carbon-carbon bonds. The bond dipole is going to be 0 because delta En is 0. And so, you know, CO2 should dissolve easily in heptane. Will CO2 dissolve easily in diamonds? What do you think? Well, like dissolves like, so it sounds like CO2 should like diamonds, right? No, it doesn't. So why doesn't CO2 dissolve easily in diamonds? Both are nonpolar. It's because of the bonds in diamond. In fact, the like dissolves like is for molecular compounds. Is diamond a molecular compound? No. Diamond is a network covalent. Network covalents are much more tricky. You have to look at those individually. And so rules like that don't apply to network covalent, just molecular. And so CO2 is not going to dissolve in diamond. So we can look at that. Okay, to sum up the bond dipoles in 3 dimensions, we need the 3-dimensional structure. In order to get the 3-dimensional structure, we have to first get the correct Lewis structure, and then we can use some VSEPR to figure out the 3D geometry of that particular Lewis structure. And so let's talk about Lewis structures, although you guys have already started generating Lewis structures. And so let's do this one. Why don't you do the Lewis structure for bicarbonate right now? Let's see what